Hello, my name is Kelsey, and welcome to my narrated presentation for the Midnight Sun Rally Challenge. And this is for MEC 434, which is AI and Data Analytics. So I was a part of a team, so it was myself and three other people working on this project, and we designed, developed, and deployed a fully autonomous lot car system powered by machine learning. So in this presentation, I will walk through the complete engineering lifecycle from mechanical integration and data collection to the AI model development, conversation, and the real-time deployment on the race day. So like I mentioned, I was a part of a team for this challenge, so it was really nice. We were able to kind of take this challenge and chunk it apart, and then kind of cohesively and collectively come together in order to make this all work. So there's a lot to it. So this is going to be kind of an overview throughout this presentation, just kind of covering my report. So the objective of this challenge was to build an autonomous lot car capable of completing the track using AI-driven throttle control. And so achieving this required full production style pipeline from mechanical design, embedded electronics, sensors, data acquisition, machine learning, model deployment, and then real-time deployment. So the system had to be reliable and race day ready, and then capable of making throttle decisions really fast. So this project was structured around several major engineering tasks. So first there was mechanical integration. So design a rigid, vibration resistant, we chose 3D printed assembly to mount the ESP32, the motor driver, and the IMU. And this ensured consistent sensor orientation and stable operation during the testing and the race conditions. So next was data collection. So we developed MicroPython system that allowed the car to be manually driven at fixed throttle values while recording data and track segments. And so capturing this data streamed over Wi-Fi to a PC, producing 12 laps of training data, and over like 8,400 samples. So I will say though, we did use Wi-Fi come race day, and then we ended up pivoting to Bluetooth, and so I'll kind of expand a little bit on that later in the next coming slides. So with the data set collected, we were able to move into kind of model development. And so we used TensorFlow and pre-processed IMU features with scaling, and one hot encoding, then trained the fully connected network for 30 epochs. And the model showed stable, there wasn't overfitting, so it was demonstrating like a pretty strong generalization to like unseen laps. So after training, the model was converted into TensorFlow Lite format just for lightweight deployment. Um, and so uh, this conversion just reduced model size, it optimized it for fast and low latency predictions. And the final step was embedded integration and deployment. So the ESP32 read IMU data at 20 hertz and then packaged it into JSON and sent it to the PC base server. And then the server ran the TensorFlow Lite model and returned throttle predictions, which the ESP32 then applied using pulse width modulation. So this architecture allowed like rapid iteration, pretty stable communication, and reliable fallback behavior if predictions were delayed. So during testing, the system demonstrated smooth, predictable autonomous behavior. The car handled straights, transitions, light turns with accurate throttle modulation. There were some times in areas where our car would kind of fishtail around one of the corners, and so we were able to adjust that. So there's just a few kind of mechanical refinements. We did reprint one of the components for the IMU, and then it just reduced vibration noise, aligned sensors. So the best autonomous lap time achieved was 14.82 seconds, with an average of 15.37 seconds. So I'll talk a little bit about race day, and then I'll throw up a video in the next slide. But race day was awesome. We were able to start at the official start time, so our car was ready to go. And it was running really consistently. We were kind of on a pace of like 1,000 laps per hour. And then the only thing that kind of we ran into really was we relied heavily on Wi-Fi connection for this. So if the car, lost power or connection or anything, it needed Wi-Fi in order to kind of communicate back and forth. And so we didn't account for a battery on this car, which was kind of the other drawback. There was some little times where the brushes would lose contact on the track, and our car would ultimately need kind of a reset altogether. And so I think next iteration would be to figure out a lightweight solution for backup battery, maybe a capacitor or something like that. And then in regards to our Wi-Fi issue, it relied on a hotspot, and so when one of our team members needed to kind of take a break and leave with that hotspot, we needed another stable hotspot to allow that Wi-Fi connection. And so we ended up pivoting and doing Bluetooth, which actually kind of made things a little more stable. So it's actually a better option, but it did take time in order to develop that. So race day was 24 hours, which was good, but it did decrease our total lap time by quite a bit. But we were able to finish the challenge strong. So hopefully in the next slide I can get this video going. Alright, so here's the video. I did capture both cars, so there's another team involved in this challenge. So you'll see both cars on the tracks. This was the first time that we got both cars racing, so it's pretty exciting. So I wanted to be sure we got it on video. So I'll go ahead and play it, and hopefully we don't need any volume on this one. So here we go. You can see them both going. Ours is quite a bit faster right there, and then the other team's is the other one going around the track. So here it is. This is the lap counter right here, so that senses every time the car goes underneath of it. And then these are the tracks for the slot cars. Alright, and then next we'll dive into the system map for this. Alright, and here is a picture of our system map that we created. You'll see the picture of our slot car right in the middle. We did kind of refine it, so wires were a little more connected, and did some cable management come race day, but that was pretty much a visual for what it ended up being. So this system map summarizes like the full architecture. So the ESP32 handles IMU sampling, JSON packaging, Wi-Fi communication, and PWM output. PC handles model interference using TensorFlow Lite, and then the motor driver applies throttle to the BRM motor, and the mechanical assembly ensures just the sensor alignment and just kind of keeps it stable. So together, all these components form kind of a cohesive production style AI controlled system that's capable of real-time autonomous navigation. So on this, you can see our track diagram here. So this was the orientation of our track that our car had to go on. Included our wiring diagram here, placement map of slot car. We have our code for how we train the AI, and then we also have the code for the AI deployed. Bill of materials, parts list, all create this system map. So thank you for listening to my presentation, and hope you have a good day.